Right now, there are literally thousands of peer-reviewed scientific papers out there utilizing artificial intelligence that are, well, they're fundamentally useless.
Yeah, it's a staggering reality.
And it isn't because the algorithms are weak, right? It's
No.
not because the data sets are too small or because researchers, lacked computing power. It's because incredibly smart people like scientists, developers, researchers simply didn't know how to ask the computer the right question.
Exactly. I mean, we are living through this era of just diagnostic muddy waters. The illusion is that if you take a massive, messy scientific problem and just sort of throw a state-of-the-art neural network at it, the math will automatically distill the objective truth.
Like magic.
Like magic.
Yeah.
But the math can only answer the specific problem formulation you feed into it. And if that formulation is logically inconsistent with the physical reality of the data, the machine will happily give you a highly accurate, completely false answer.
Wow. Well, welcome to today's deep dive. We are thrilled you're here with us. Whether you're an undergraduate taking your very first steps in data science, a PhD or postdoc wrestling with the design of your thesis, or an industry professional actively deploying machine learning models to production, this one is definitely for you.
It really is.
You're unpacking this highly intense, deeply academic facilitator script titled Problem Formulation and Evaluation Design.
It's essentially a survival guide, to be honest. It's a facilitator script for a 100-minute, highly serious academic workshop designed to force practitioners to just slow down.
Yeah, slowing down is the hardest part.
It really is. The entire mission of this document, and our mission with you today, is to explore the epistemic backbone of science. We're going to look at how you actually transition from a vague human curiosity into a rigorously testable mathematical claim.
Okay, let's unpack this, because the core premise hits like a ton of bricks. It completely shatters that whole Silicon Valley move fast and break things mantra.
Oh, completely.
The text argues that problem formulation is not just some administrative, preliminary step before you get to the real work of coding. Problem formulation is the ultimate scientific act.
And skipping it leads to what the text identifies as the single most common failure mode in modern applied data science. It's this instinct that plagues everyone from undergraduates to seasoned industry veterans.
The overwhelming urge to jump straight from downloading a data set to fitting a model.
Yes, exactly that.
Let's visualize this because, if you're listening to this and you've ever written a line of Python, your palm might be sweating right now.
Yeah.
You find a data set, you download the CSV file, you open up your Jupyter notebook.
Classic workflow.
Right. You load the data in using pandas, and then, almost like a muscle memory reflex, you immediately chop that data into a training set and a testing set, and you just instantiate a model. Random forest, gradient boosting, whatever.
Oh, it's trendy.
Yeah, just start watching the loss curve go down and the accuracy go up.
And you feel incredibly productive, right? You're writing code, the computer is humming, the metrics look fantastic. But the script points out the fatal flaw here. You are doing all of this computation, optimizing hyperparameters, and only stopping to ask what question you actually answered after the fact.
Like shooting an arrow and then painting the target around it.
Spot on. You are letting the code dictate the science, rather than the science dictating the code.
But hold on, let me challenge that for a second. Because the fundamental tool you just described, the random split cross-validation, that is literally the absolute gold standard taught in every computer science class in the world.
It is, yeah.
Like, if I take my data, randomly hold out 20% of it, train the model on the 80%, and it successfully predicts the 20% it has never seen before.
Right.
Haven't I mathematically proven that the model found a true, generalizable pattern?
Well, you've proven it found a pattern in that specific matrix, but you haven't proven it found a scientific truth.
Wait, really?
Yeah. In fact, in the hard sciences, that random split you just defended is often the exact mechanism that destroys your scientific validity.
That's crazy to think about.
The script outlines this beautifully with a water data example. Let's look at the mechanics of why the random split fails so spectacularly here.
Okay, let's do it. Walk me through the mechanics.
Imagine you're trying to build an AI to predict E. coli exceedances in a city's drinking water supply. Your predictor is rainfall data, right? Because heavy rain washes agricultural runoff into the rivers.
Makes logical sense. Rain goes up. A few days later, bacteria goes up. I want the model to learn that lag.
Right. You have a massive spreadsheet. Column A is the date, column B is the millimeters of rainfall, and column C is the E. coli concentration measured that day.
Okay, I'm visualizing the spreadsheet.
Good. But watch what happens to the physics of your data when you use that quote-unquote gold standard random split. The computer doesn't know what a day is, it just sees rows.
Yeah, it's just numbers.
When you call your train test split function, it shuffles the index of that spreadsheet like a deck of cards. Now look at your training set. You might have the data from Tuesday in there, but because of the shuffle, you also have the data from Thursday of that exact same week in your training set.
Oh, I see it.
You see the problem.
Yeah. If my model is trying to learn the relationship between Tuesday's rain and Wednesday's water quality, but I've randomly fed it Thursday's water quality as part of its historical training context,
Yep.
I'm bleeding the future into the past.
You have built a time machine, not a predictive model.
Wow.
It's called catastrophic data leakage. The loss function of your neural network is incredibly greedy. I mean, if it can find a shortcut to minimize error, it will absolutely take it. It will look at Thursday's data to back calculate Wednesday's prediction.
And your metrics on paper will be flawless.
Exactly. You'll have 99% accuracy. You might even publish a paper claiming you solved municipal water safety.
But the second I deploy this model in the real world, where I'm sitting on a Tuesday and Thursday literally hasn't happened yet, the model will completely collapse. Because that future data it learned to rely on isn't there to leak anymore.
Exactly. And this happens because the concept of a random split assumes your data is IID, independent and identically distributed.
Right, the standard assumption.
Yeah. In computer science, if you're classifying images of cats and dogs, one picture of a cat has absolutely no physical relationship to the next picture of a dog. They're independent. So random shuffling is fine.
Doesn't matter what order you look at them.
Right. But in physical systems like water flowing down a river, weather patterns, chemical reactions, the data is fundamentally dependent. Time flows forward. Geography is linked.
So by treating physical science data like it's a folder of cat pictures, we're generating these models that are absolute masters of a closed loop, but entirely useless the moment they touch reality.
The script calls this artificial, unearned generalization. And what's fascinating here is that it extends far beyond just time.
Give me an example.
Look at the chemistry example in the text, predicting the percentage yield of a chemical reaction. Chemists use molecular databases built around scaffolds. Think of a scaffold as the core structural chassis of a molecule.
Oh, like a car chassis. A manufacturer builds a base frame, and then they tweak it. They put a sedan body on one, a hatchback on another, change the engine slightly, but the underlying metal skeleton is identical.
That is a perfect analogy. In chemistry, scientists take that core molecular chassis and make tiny, incremental tweaks to the functional groups hanging off it, creating hundreds of slightly different variations of the same core molecule.
Okay, I'm with you.
Now, what happens if you take that data set and run your standard random 80-20 split?
I mean, I'm going to end up with variations of the exact same chassis in both my training bucket and my testing bucket.
Yes. And what does the model actually learn?
It doesn't learn quantum chemistry. It just memorizes the chassis.
Right.
It's like training an AI to be a universal vehicle detector by showing it 10,000 pictures of a 2015 Honda Civic painted in different colors. The test set is just a blue 2015 Honda Civic. The AI says, yep, that's a vehicle, and you think you've solved computer vision.
Right. You think you're a genius.
But the second a pickup truck or a bicycle rolls into the frame, the model is completely blind.
In data science, we call this a failure to handle covariate shift. The distribution of your input features, the X variables in the real world, will inevitably shift away from the distribution in your training set.
And if your problem formulation didn't account for that shift,
Your model is just recognizing the Honda Civic.
man. So if the instinct to just open the notebook and, pour the concrete everywhere is this dangerous,
Yeah.
how do we stop ourselves? How do we force ourselves to build a blueprint before we code?
Well, the text introduces a rigid mental structure called the research problem ladder.
This is that epistemic backbone we talked about at the start.
Yes. There are 5 rungs: phenomenon, question, hypothesis, operationalization, and metric. Every single valid scientific modeling project sits somewhere on this ladder, but the human instinct is to leap directly from the phenomenon straight to the metric.
Completely skipping the brutal intellectual labor of the middle rungs.
Exactly. You just skip right over it.
Okay, let's climb it rung by rung. We'll stick with the water example because it really grounds the theory well. Rung 1, phenomenon.
Right. So a phenomenon is a state of reality that exists entirely independent of you, your sensors, or your computer. In our case, the phenomenon is post-rainfall contamination.
So it rains, dirt, and agricultural waste wash into rivers, the water becomes contaminated.
Yes, this is an objective physical reality. It happens whether a scientist is looking at it or not.
Simple enough. Run 2. Question. This is where human curiosity enters the chat, right?
Yes. You observe the phenomenon and you ask a qualitative human language query. Does rainfall actually increase the risk of E. coli infection for people drinking this municipal water?
Which still feels like a standard middle school science fair setup. But rung 3 is where the boundaries start to close in. Hypothesis.
Right, because a question is open-ended. A hypothesis is a highly specific, testable claim that can be mathematically proven false.
You can't code a question.
Exactly. So we transition from does rainfall increase risk to a specific assertion. The probability of an E. coli exceedance increases significantly within a 72-hour window following a heavy rainfall event.
We've locked in a time boundary, 72 hours, and a directional relationship probability increases.
Yes.
Here's where it gets really interesting. Rung 4. Operationalization. Just reading this section of the script, you can literally feel the anxiety of 1,000 graduate
Oh,
students.
absolutely.
Because this is where abstract theories go to die against the rocks of hard data.
Operationalization is the crucible of science. It is the exact moment you must translate the human words of your hypothesis into the literal columns and rows of a dataset. You have to define your variables with absolute, uncompromising mathematical precision.
Let's invent a hypothetical PhD student here. Let's call her Sarah.
Okay, Sarah.
Sarah has spent 2 years building a complex theoretical model about how agricultural runoff affects drinking water. She has a beautifully articulated hypothesis, but now she has to operationalize the concept of dirty water. She looks at the municipal sensor data and she realizes the sensors in the river don't actually measure E. coli, they measure turbidity.
Which is the cloudiness of the water, how much light scatters when it hits suspended particles.
Right. So Sarah thinks, okay, cloudy water usually means dirty water. I'll just use turbidity as my proxy variable for E. coli.
Which happens all the time.
What is the mathematical and scientific consequence of that operationalization?
The consequence is that her entire 3-year thesis is now predicated on a massive epistemic gap.
Wow.
Turbidity is not E. coli. Heavy rain might wash entirely sterile silt into the river. The turbidity spikes, the water is incredibly cloudy, but there is zero bacteria. Or, conversely, a highly concentrated, clear chemical runoff could introduce deadly pathogens without changing the cloudiness at all. If Sarah trains a neural network to predict turbidity, but she writes her paper claiming she is predicting bacterial infection risk, her science is fundamentally flawed at rung 4.
She is asking the computer to predict the shadow and telling the world she predicted the object.
That's a beautiful way to put it. Precisely. To operationalize correctly, she must explicitly define the target variable and the predictor variable.
And the text gives a really rigid standard for this.
Yes. The target must be operationalized as E. coli concentration, strictly greater than 0 colony-forming units per 100 milliliters.
Very specific.
And the predictor can't just be heavy rain. It must be operationalized as total accumulated rainfall in millimeters, calculated over trailing 24, 48, and 72-hour rolling windows prior to the exact timestamp of the water sample.
And once you have mapped reality to those literal columns of numbers, you finally reach run 5. Metric. How truth is evaluated.
The metric is the exact mathematical formula that scores the game. Once your neural network spits out a prediction based on those operationalized variables, how do you judge if it's actually any good?
The script uses recall at the regulatory threshold for the water example, which we are going to dive deep into shortly because the math behind metric selection is just fascinating.
It really is.
But just looking at the journey from phenomenon to metric, it becomes so clear why people skip it. Climbing this ladder forces you to admit what you don't know and what your data physically cannot do. It forces you to realize that you might not be allowed to ask the question you wanted to ask.
Which is a perfect transition into the most philosophically rigid part of the facilitator script, the problem framing taxonomy.
Let's get into it.
Once you're on the ladder, you have to commit to a specific problem frame. The script outlines 4: descriptive, predictive, explanatory, and causal. And it states unequivocally, this is not a modeling choice you can tweak later in your Python code. It is a scientific commitment.
A commitment means you are locked in. You are declaring to the scientific community exactly what flavor of truth you are attempting to produce. Let's start at the base of the taxonomy. The descriptive frame, the driving question here is just, what patterns exist?
Right. Descriptive framing is heavily stigmatized in modern academia and industry because, well, it isn't flashy, it doesn't use massive predictive models, but it is entirely appropriate when you have a small data set or purely observational data where you didn't intervene or run an experiment. You are simply taking the data and mapping the reality of it.
Like plotting the seasonal variation turbidity across 5 different testing sites over a year.
Yeah.
Or in chemistry, charting out the distribution of reaction yields based on different solvent classes. You're just saying, look, here's what happened.
And the script provides a brilliant defense of this. It says, if your data set cannot support prediction, descriptive analysis is not a failure. It is honesty.
I love the sentiment there. But let's be incredibly real for a second. If you are a postdoc listening to this, you know that honest descriptive analysis does not get you published in Nature.
No, it doesn't.
And if you're in industry, going to your CEO and saying, our $1 million AI team has successfully described the past, will get you fired.
Absolutely.
The entire incentive structure of the modern world demands prediction and causality.
You're hitting on the exact systemic pressure that causes so much bad science. The pressure to force data up the taxonomy ladder is immense. So let's look at what is mathematically required to validly claim the next frame: predictive.
Where the question is, what will happen?
Right. And the script puts heavy guardrails around this. Prediction is only scientifically valid if you are explicitly evaluating your model across a boundary of the unseen.
A boundary of the unseen. Explain that.
Prediction is about proving your model's logic holds up when it is deprived of context. You must forecast a future time that hasn't occurred, or predict the properties of a chemical compound that has never been synthesized, or forecast outcomes at a new physical geographic site. If your evaluation methodology doesn't strictly enforce that boundary, you aren't predicting, you are just memorizing.
Memorizing the past.
Exactly.
Okay, moving up again, we hit the explanatory frame. The question shifts from what will happen to what variables are associated. How is this fundamentally different from prediction? Don't predictive models use associations to make their guesses?
They do, but the goal is different. In a predictive frame, you largely treat the model as a black box. If I feed a deep neural network satellite imagery and it accurately predicts crop yields for next year, I might not care exactly which pixels the model is looking at, as long as the future prediction is consistently right.
Okay.
But in an explanatory frame, peering inside the box is the entire point. You want to understand feature importance.
So in the water context, an explanatory question would be, which specific land use variables, like, say, the ratio of paved concrete roads to open agricultural fields, correlate most strongly with high turbidity in adjacent rivers?
Exactly. You are trying to map the web of relationships. But this frame comes with the oldest, most ignored warning label in statistics. Association is not causation.
Right. Correlation does not imply causation.
Yes. Just because your model finds a massive, statistically significant mathematical link between paved roads and dirty water, it does not mean the roads caused the dirt.
Which brings us to the Holy Grail. The frame that everyone wants and the one that ruins the most careers.
Causal.
Causal. The question here is, what would change under intervention?
Causality is the ultimate prize because it dictates policy and action. A city council wants to know, if we spend $50 million to ban a specific fertilizer, will it actually cause nitrate levels in our groundwater to drop?
And to answer that, we have to look at the math of causality versus observation. Why can't a sufficiently massive neural network trained on millions of rows of historical farming and water data just figure out the causal link?
Because of the fundamental limits of observational math, a neural network at its absolute core is a sophisticated curve fitter. It learns conditional probabilities.
Right.
It learns the probability of Y occurring, given that we observed X occurring in the historical data. In math notation, that is P of Y given X. But causality requires a completely different mathematical operator. It requires the do calculus, pioneered by Judea Pearl.
Okay, do calculus.
Yes. Causality is the probability of Y occurring given that we physically intervene and force X to happen. That is P of Y given do X.
Okay, let me make sure I'm tracking this. Let's use the fertilizer example from the text. I have a massive data set of farms. Some use fertilizer A, some don't.
Yeah.
I observed that farms using fertilizer A have much higher nitrate levels in their runoff. The conditional probability, P of Y given X, says they are highly linked. Why can't I say fertilizer A causes the nitrate spike?
Because of confounders, hidden variables that influence both the cause and the effect. You didn't run a randomized controlled trial. You just observed existing farms.
Right.
What if the fertilizer is incredibly expensive? That means only wealthy corporate farms can afford it. And those wealthy farms also happen to use massive industrial irrigation systems that wash more soil into the river.
Ah. So it isn't the chemical makeup of the fertilizer causing the nitrates. It is the industrial irrigation that happens to always travel alongside the expensive fertilizer.
Exactly. The irrigation is the confounder. If the city council bans fertilizer A based on your model, the farmers will just switch to fertilizer B, keep the exact same industrial irrigation systems, and the nitrate levels won't drop a single point. $50 million wasted.
That is a brutal realization. So if I have that observational farming data, what question am I actually allowed to ask?
You have to step down the taxonomy ladder. You must accept an explanatory frame. You ask, is fertilizer application associated with higher nitrate levels? You do not use the word cause.
But people do it anyway. They try to brute force the math.
They do. And if we connect this to the bigger picture, the script delivers one of the most sobering reality checks I have ever read in an academic text. It says, you cannot fix a causal mistake by tuning hyperparameters.
That hits hard.
It really does. It doesn't matter if you add 20 more hidden layers to your neural network or change your learning rate. No amount of algorithmic optimization can magically invent a randomized controlled trial that you never ran in the physical world.
The math cannot save you from a logical fallacy.
Exactly. And this leads to the script's major warning. Most open datasets invite causal questions. Very few can actually answer them.
Okay, so let's assume we survived the taxonomy. We resisted the urge to fake causality. We committed to a valid predictive frame. Now we have to sharpen the focus. We're moving into the mechanics of target variable design and scientific baselines.
Right. This is where we revisit operationalization, but we look at how the specific mathematical shape of your target alters the learning process of the algorithm itself. The script insists that a target requires 4 things: a name, a unit, a threshold, and an observation frequency.
Let's go back to turbidity, the cloudiness of the river water. I have 2 choices for how to frame this target for my model. Choice 1. I keep it as a continuous variable. I ask the model to predict the exact continuous number. Will the turbidity be 2.5 NTU? Will it be 14.8 NTU? I'm using regression.
Or choice 2,
Yeah.
you binarize it. You apply a regulatory threshold, like say 5 NTU, which might be the legal limit for safe drinking water. Now, your target is entirely binary, 0 or 1, safe or unsafe. You are using classification.
Why does this choice matter so much to the actual machine learning process? What is happening under the hood?
It completely changes how the loss function calculates error, which means it changes how the model updates its internal weights. If you use a continuous target, the model is punished based on magnitude. If the true turbidity is 500, like a catastrophic mudslide, and the model predicts 5, it receives a massive error penalty. It learns that extreme events require big adjustments.
But if I use a binary threshold to a classification model, a turbidity of 5.1 is an unsafe one. And a turbidity of 500 is also just an unsafe one.
Exactly. You have purposefully thrown away all magnitude information. If the model predicts unsafe for a 500 NTU event, its loss function registers 0 error. It thinks it did a perfect job.
Wow.
It has no idea that a catastrophic mudslide just destroyed the water filtration plant because you hid the magnitude behind a binary threshold.
That is wild. You simplify the evaluation, but you literally blind the model to the severity of reality. The same applies to chemistry, right?
Yeah.
Predicting the exact 68% yield of a reaction versus just predicting success because it crossed a 50% threshold.
Yes. Changing the shape of the target changes what the model considers to be truth. And once you lock that in, you must establish a baseline.
Baselines.
And the script's approach to baselines is incredibly refreshing, particularly for those of us tired of AI hype.
Right, because usually in ML papers, the baseline is just a straw man. The researcher runs a basic, untuned linear regression. It performs terribly, and then they unveil their massive transformer model that performs 20% better, and everyone claps.
The script rejects that entirely. It defines a baseline not as a weak algorithm, but as the answer to a specific human question. What would a reasonable scientist predict without using machine learning at all?
I love the concept of the reasonable scientist. Give me the mechanics of some of these baselines.
The most powerful one in physical systems is the persistence baseline. If you are predicting the decay of chlorine in a municipal pipe network today, the persistence baseline is simply guessing, whatever the value was yesterday.
Because physical infrastructure doesn't usually experience wild, random swings overnight. Yesterday's reality is a highly probable anchor for today's reality.
Precisely. Another is the seasonal mean. If I am predicting river turbidity in April, My baseline is just taking the historical average of every April over the last 10 years.
Makes sense.
In chemistry, an expert heuristic baseline might just be calculating the historical average yield for a specific class of solvent reactions. It requires absolutely zero machine learning.
I've got an analogy for this. It's like comparing machine learning to a multi-million-dollar prototype sports car. It has a massive V12 engine, incredibly complex onboard computers, capable of doing 200 miles per hour. And the baseline, the seasonal mean, is a bicycle.
Oh, okay, I like where this is going.
If you put them both on an empty, perfectly paved, closed racetrack, which is exactly what most sanitized academic benchmark datasets are, the sports car obliterates the bicycle. It's not a competition.
But the real world is not a closed racetrack.
Exactly. The real world of applied science is trying to get across downtown Manhattan during rush hour traffic in the pouring rain. Suddenly, that multi-million-dollar sports car is stuck at a red light behind a garbage truck. Its complex sensors are confused by the rain. Its engine is overheating.
Yeah.
Meanwhile, the reasonable scientist on the bicycle just hops into the bike lane, pedals right past the gridlock, and gets to the destination 20 minutes faster.
That is a phenomenal way to visualize it. The complex AI gets bogged down by the noise, the variance, and the confounders in the real-world data, while the robust, simple heuristic, the bicycle, cuts through the noise because it relies on fundamental physical averages.
And this leads to a punchline in the text that should honestly be framed on the wall of every data science department in the world. If ML cannot beat a baseline, the dataset is telling you something.
This is a critical moment for industry listeners.
Yeah.
Imagine you are the lead data scientist at a pharmaceutical company. You just spent 6 months and burned $1 million of cloud compute to train a massive graph neural network to predict reaction yields.
Sounds stressful.
You present your findings, and a senior chemist stands up and shows that simply using an Excel spreadsheet to guess the historical average of the molecular chassis, a calculation that costs $0, is actually more accurate than your multi-million-dollar model.
Oh, man. That is a resume-generating event. You are looking for a new job.
But scientifically, it is a triumph of truth. If your state-of-the-art model cannot beat the bicycle, the data is screaming at you. It is telling you that the complex patterns you are trying to extract simply do not exist in the numbers you collected, or your problem formulation is so flawed that the model cannot find them. The baseline is the ultimate scientific control.
Okay, so we have our target, we have our bicycle to race against, now we have to design the racetrack itself. We have to prove the model learned something real.
This brings us to what the text calls the most misunderstood scientific decision of all: evaluation design.
This is the conceptual peak of the facilitator script. It makes a profound statement. Your train test split is not just a utility function. Your train test split is your generalization theory. I need to stop and highlight this because I know for a fact that 99% of people learning to code just view train to split as a necessary piece of plumbing. You import it from scikit-learn, you set test size equals 0.2, and you never think about it again.
But the script forces you to realize that every time you split data, you are declaring a philosophical belief. The text says, your split says where the future comes from. How you divide the data physically encodes how you believe knowledge transfers from the known to the unknown.
So if my data has physical structure, my split has to respect that structure. Let's revisit the temporal split.
In water quality forecasting, time is the dominant axis. You cannot randomly shuffle. You must make a clean chronological cut, train the model exclusively on data from 2018 to 2021, lock the model, then test it purely on data from 2022.
Okay.
If it succeeds, your generalization theory holds. The model learned the physics of water, not the specific quirks of 2020.
But what if I wanted to play this water sensor to a brand new river? Time isn't the hurdle there. Geography is.
Then you must use a site holdout split. Suppose you have data from 10 monitoring stations. If you randomly mix them, the model learns the unique geographic signature of all 10. It memorizes the map.
Right.
To prove it generalizes, you must train it on stations 1 through 8 and test it on stations 9 and 10, which the model has never seen.
Let's bring this back to the Honda Civic example in chemistry, the molecular scaffolds.
Yeah.
Because the scaffold split in drug discovery is fascinating.
Drug discovery is incredibly expensive. You synthesize a new molecule in a wet lab, test it, it fails. Millions of dollars gone. You want an AI that can imagine entirely novel molecular structures that might cure a disease, things humans haven't even thought of.
But if I use a random split on my database of known drugs,
You're putting the Honda Civic in both buckets. The AI memorizes the core chassis. It gets a 99% accuracy rate on the test set, but it has only learned to recognize minor variations of drugs that already exist. It hasn't learned the fundamental quantum mechanics required to evaluate a completely new structure.
So how does a scaffold split mathematically force the AI to learn chemistry?
An algorithm groups all the molecules in your dataset by their core chassis. It then mandates that all molecules sharing chassis A, B, and C go strictly into the training set, and all molecules built on chassis X, Y, or Z go strictly into the test set.
It is brutal. You are purposely depriving the model of the structural hints it needs to cheat. You are making the test infinitely harder.
Exactly. You are forcing the model to infer the underlying rules of chemistry because the superficial shapes it memorized during training are entirely absent from the test set. If the model survives the scaffold split, you have a massive scientific breakthrough. If it fails, you know your AI was just memorizing shapes.
So what does this all mean? I want to pause and synthesize this because this completely unravels a lot of standard operating procedures. The random split is mathematically invalid for almost all physical science data.
It is scientifically hazardous. Random splits are only valid when your observations are entirely independent, which we established is incredibly rare in the physical world. If you randomly split dependent data, you are not testing a model. You are just quantifying how effectively the algorithm memorized the background noise.
Okay, so the split dictates how hard the test is and prevents the model from cheating. But once the test is taken, the model is going to make mistakes. No model is perfect. How do we judge the gravity of those mistakes? This brings us to the final hurdle: metrics as value judgments and freezing the contract.
This is where the cold, abstract math of machine learning suddenly becomes intensely human. The script explains that a metric, the mathematical formula you use to calculate your error rate, is not a neutral equation. A metric is an ethical value judgment because metrics encode the real-world cost of errors.
Let's walk through the math of this because it's brilliant. We are back to predicting E. coli in the water. It is a binary classification, safe or unsafe. There are two ways the model can be right and two ways it can be wrong.
The errors are what matter. We have false positives and false negatives. A false positive means the model screams unsafe, but the water is actually perfectly clean.
What is the cost of that error in the real world? The city issues an unnecessary boil water advisory. People are annoyed. A local coffee shop loses a day of revenue. The mayor gets some angry emails. It's bad, but it's, administrative friction.
Now look at the false negative. The model calmly states safe, but the river is actually swarming with highly infectious E. coli.
The cost of that error is devastating. A community drinks the water, hundreds of people end up in the emergency room, vulnerable people might die. The real-world consequence of a false negative is exponentially morally worse than a false positive.
And here is the trap. This raises an important question. If you evaluate that model using basic accuracy, which is just the total number of correct guesses divided by the total number of guesses, you are treating both of those errors as mathematically identical.
Right.
By choosing accuracy, you are implicitly making a value judgment that annoying a coffee shop is morally equivalent to poisoning a child.
That is a staggering way to frame it. So what metric do I have to use to encode the correct human values?
The script mandates that for this asymmetric risk, you must optimize for recall. Recall is a metric that specifically calculates how many of the actual positive cases, the real E. coli spikes, your model successfully found.
So it heavily penalizes the algorithm for missing a threat.
Exactly. It forces the model to become hypersensitive. It might throw more false alarms, which are false positives, but it will rarely miss a real contamination event.
And this asymmetric math applies to continuous numbers in chemistry too, right? The text compares two regression metrics. RMSE root mean square error, and MAE mean absolute error. Walk me through the mechanics of RMSE. Why does it act like a magnifying glass for outliers?
It is in the name. Root means square error. Before it averages the errors, it squares every single mistake the model makes. Let's do the mental math. If your model misses the chemical yield by a tiny margin, say 2%, you square that. The penalty is 4. Small error, small penalty.
But if the model misses a prediction by 10%,
you square it. The penalty explodes to 100. Because of the squaring function, RMSE scales non-linearly. It punishes large errors astronomically harder than small errors.
so if you are predicting a chemical reaction where being slightly off just means a lower yield, but being massively off means the reactor explodes and destroys the lab,
Yeah.
you must use RMSE. You want an algorithm that is terrified of making large mistakes.
Exactly. MAE, on the other hand, just takes the absolute value. An error of 10 is just 10. It treats all errors proportionally. Choosing between RMSE and MAE isn't a coding preference you look up on Stack Overflow. It is you, the scientist, defining the real-world consequences of your algorithm's failure.
And to make sure practitioners actually internalize this immense responsibility, the text outlines a physical workshop environment. I want to talk about this because the psychology of this academic session is intense. They use something called the problem statement canvas.
It is a crucible. The facilitator hands everyone a worksheet with incredibly strict rules. The very first box you must fill out before you are allowed to write a single word about neural networks or AI is the DOI, the digital object identifier of your dataset.
You literally have to prove your data exists in the physical world before you can dream about algorithms.
Yes. And every single justification you make for your taxonomy frame, your split strategy, and your metric must explicitly reference the structural properties of that specific data. The canvas even has a mandatory not feasible box.
Yeah.
You are forced to write down exactly what your data cannot do.
And then comes the peer review, the gallery walk.
The script instructs the facilitator to enforce rigorous, uncompromising academic critique. This isn't friendly brainstorming. Participants use color-coded notes, green for sound logic, red for fatal scientific flaws.
And the text tells the reviewers exactly how to attack. You don't just say, I think random forests are better here. You say, your train test split does not match the physical boundaries of your problem framing. Or, your chosen metric is mathematically misaligned with the real-world objective you claim to be solving. It is a gauntlet of logic.
And surviving that gauntlet leads to the ultimate culmination of the session, freezing the scientific contract. By the end of this 100 minutes, the researcher must have a frozen target definition, a frozen taxonomy frame, and a frozen splitting strategy.
Freezing the contract. I love the permanence of that phrase.
It has to be permanent. The facilitator delivers a final absolute warning. From here on out, all preprocessing and all modeling must respect the scientific contract you just froze.
Meaning I can't cheat later. If I run my models and my recall score is terrible, I cannot go back and secretly change my metric to accuracy just to make the numbers look good enough to publish in a journal.
If you change the metric to hide the failure, you break the contract. If you abandon your temporal split for a random split because it inflates your score, you break the contract. And if you break the scientific contract, your AI is no longer doing science. It is just generating marketing material.
Which brings us to the end of our journey through this phenomenal academic script. We have covered a massive amount of conceptual ground today, scaling from the absolute basics to the peaks of epistemic theory. Let's synthesize exactly what we have unpacked.
We started by identifying the ultimate trap. The seductive, scientifically hazardous instinct to download a dataset and immediately fit a model using random splits. We walked through the catastrophic consequences of data leakage and how algorithms will cheat time and memorize structures if you let them.
We learned how to slow our brains down by climbing the research problem ladder, moving from an abstract phenomenon through the brutal crucible of operationalization, translating human theories into rigid mathematics.
We explored the problem framing taxonomy, realizing that descriptive, predictive, explanatory, and causal frames are binding scientific commitments, fundamentally governed by the math of observation versus intervention. We established the vital importance of the bicycle, the reasonable scientist baseline that keeps our million-dollar models honest.
We redefined the train test split not as a line of code, but as our generalization theory, a declaration of where the future comes from, be it time, geography, or chemical structure. And finally, we confronted the moral weight of metrics, recognizing that mathematical formulas encode the real-world costs of who gets harmed when our models inevitably fail.
True data science, whether you are an undergraduate or a lead engineer, is not a race to write the most complex code. It is the rigorous, exhausting, but absolutely essential process of defining the parameters of truth before you ever touch a keyboard.
It is about drawing the blueprint before you pour the concrete. We have spent an hour exploring the deep mechanics of how we formulate problems for machines to solve. But as we wrap up this deep dive, there is one lingering, slightly haunting idea embedded in the source material that I want to leave you to mull over.
It's a big one.
The text explicitly warns that most open, highly accessible data sets naturally invite us to ask complex causal questions. We desperately want to know why things happen and how to intervene to fix the world's problems. But the mathematical reality is that very few of these data sets possess the structural integrity to actually answer those causal questions safely. We are told, quite rightly, that we must strictly limit our ambition to the boundaries of our data.
Right.
But if our available data sets strictly dictate the level of questions we are scientifically allowed to ask, are we systematically limiting the horizon of human discovery simply because we only want to ask the questions that our current, flawed, historically limited data sets can easily answer?
That is the question.
Think about that the next time you open a Jupyter notebook. Until next time, keep diving deep.